Welcome to Multivariate Calculus. Today, we are going to explore a truly powerful mathematical technique called the change of variables. If you have ever faced an integral with boundaries that seem completely impossible to work with, this is the tool that will save you. By the end of this lesson, you will understand how to reshape space itself to make your calculations beautifully simple. To understand why we need this, imagine trying to measure the exact area of a perfectly round pizza using a square grid. You would have a terrible time counting all the tiny, broken square pieces around the curved edges. But if you slice the pizza from the center outward, measuring the angle and the radius, the math becomes incredibly easy. In calculus, when a shape is too ugly to integrate using standard flat grids, we switch to a custom-made grid. We invent new variables that perfectly match the shape, unfolding a twisted region into a neat rectangle. Now that we understand the goal of changing our grid, we have to address a physical consequence. When we stretch or squish our grid to make a shape simpler, the physical sizes of our tiny area pieces change. We must mathematically correct for this distortion so our final total remains accurate. This conversion fee is called the Jacobian. Think of it like a currency exchange rate when traveling. If our new grid stretches the area to be 3 times larger, the Jacobian will be 3, ensuring we are still calculating the true original area. This brings us to the mathematical definition of our scaling factor. The Jacobian is calculated using a determinant of partial derivatives. Conceptually, it measures how much one specific variable changes when we tweak another, keeping everything else frozen. In this formula, j of u and v is the Jacobian. The variables x and y are our old coordinates and u and v are our new ones. By cross-multiplying the partial derivatives of the old variables with respect to the new ones, we find the exact stretching multiplier needed at any specific point in space. If the new variables warp the space more, this determinant increases. With our scaling factor defined, we can now put it all together into the master formula for changing variables in a double integral. On the left, we have the integral over our original complicated region R. On the right, we replace every x and y with their new u and v formulas, integrating over the simple new region S. Crucially, we must multiply by the absolute value of the Jacobian because physical area cannot be negative. The old area pieces, dx dy, are completely replaced by the new, properly scaled area pieces, du dv. If the Jacobian is large, it means a small change in u and v covers a large area in x and y. Before we move on, let us see this transformation with a concrete visual. On the left side of this diagram, you see the original x and y axes containing a warped, difficult region R. Notice the tiny area piece labeled dx dy. Through our transformation T, we map this entire shape onto the u and v axes on the right, where it becomes a clean, flat rectangle S. The tiny area piece is now du dv. The Jacobian we just discussed is the mathematical bridge that ensures the highlighted area on the left is correctly scaled to match the highlighted area on the right. Now that we have our master formula and a clear visual understanding, let us apply this to a real problem. We are asked to evaluate the double integral of x plus y over a slanted parallelogram. Integrating this directly using standard x and y limits would be a nightmare because the boundaries are angled lines. Instead, we invent new variables based on the boundary equations themselves. We let u equal x plus y and v equal x minus 2y. This brilliant substitution turns our slanted parallelogram into a perfect flat rectangle where u simply goes from 1 to 4 and v goes from 0 to 3. Continuing with our setup, we need to find the Jacobian. However, to take the required partial derivatives, we need x and y isolated by themselves. We cannot differentiate them in their current form. So we solve this system of equations. By subtracting the v equation from the u equation, the x variables cancel out completely, leaving us with 3y. Dividing by 3 gives us y in terms of u and v. We then substitute this new expression for y back into our first equation to isolate x. Now we have both x and y defined entirely by our new variables, and we are ready to calculate the stretching factor. With x and y isolated, we take their partial derivatives and place them into the Jacobian matrix. Because our transformation equations are simple linear lines, all of the derivatives are just constant fractions. For instance, the derivative of x with respect to u is simply 2/3. We calculate the determinant by cross-multiplying these fractions and subtracting. The result is negative 1/3. Remember, the master formula requires the absolute value of the Jacobian, so our actual scaling factor will be positive 1/3. This tells us our new flat rectangle is mathematically 3 times larger than the original slanted parallelogram. We are now ready for the final evaluation. We set up the new simplified double integral. The original function x plus y is simply replaced by our new variable u. We pull the constant 1/3 scaling factor out to the front to keep the math clean. First, we integrate u, which gives u squared over 2, evaluated from 1 to 4. This simplifies to 15 halves. Finally, we integrate this constant with respect to v from 0 to 3. Multiplying the fractions together gives us our final answer of 15 halves. By changing variables, we turned a nearly impossible geometry problem into a straightforward calculation. Now that we have successfully used the Jacobian formula in a concrete example, let us look at a fundamental proof of how it works for polar coordinates. When we switch from rectangular coordinates to polar coordinates, the area element dx dy famously becomes r dr d theta. Let us prove exactly why that extra r appears. We start with the standard conversion formulas, x equals r cosine theta and y equals r sine theta. We take the partial derivatives of x and y with respect to both r and theta. These 4 derivatives will form the entries of our Jacobian matrix. Continuing with our derivation, we place these 4 partial derivatives into our Jacobian matrix. The top row contains the x derivatives and the bottom row contains the y derivatives. To find the true geometric scaling effect, we must calculate the determinant of this 2 by 2 matrix. We do this by cross-multiplying the top left term by the bottom right term and then subtracting the product of the top right and bottom left terms. This standard matrix operation is crucial because it captures exactly how the grid stretches and warps when we move from a world of straight lines into a world of circular angles and radii. This brings us to the final result of our proof. Multiplying the terms out gives us a squared cosine term and a squared sine term. The double negative on the sine term turns into a positive plus sign. We can factor out the common variable r from both terms, which beautifully reveals a famous trigonometric identity inside the parentheses. Since the sum of a squared cosine and a squared sine is always exactly 1, the entire expression simplifies to just r. This proves that the stretching factor when moving to polar coordinates is exactly the radius, which is why we must multiply by r to keep the area accurate. So we have proven that the Jacobian perfectly corrects our area calculations. This brings us to why this matters outside the classroom. The change of variables technique is an absolute lifesaver in advanced physics and engineering. In the real world, objects are rarely perfect squares aligned to a flat grid. If an aerospace engineer needs to calculate the center of mass of a curved airplane wing, or a meteorologist wants to model the swirling winds of a hurricane, standard coordinates would be too complex for even computers to solve efficiently. This technique allows scientists to adapt their math to fit nature. To wrap up our lesson, let us review the most important ideas. Changing variables is like looking at a complex problem through a custom-made lens that makes it look simple. We swap our difficult x and y coordinates for new u and v coordinates that flatten out our boundaries. But to ensure our final answer remains physically true, we must always calculate the Jacobian determinant. This acts as a mandatory scaling factor to correct for any stretching or squishing of the area. You now have the tools to transform almost any impossible shape into an easy to solve rectangle. Great job!